Welcome to our course again. So, here is we are on the 6th lecture. So, here we are going to speak about continuous functions. We are not going to fix up and try to always find functions which are continuous. If I can borrow the name from Professor Corner, I would like to call this course really the course for the ambitious, calculus for the ambitious, in the sense that here we are largely bothered about concepts. Of course, there will be certain aspects of calculus where examples would be given, but this is not a course where, again I want to repeat for those who would like to come into the exams for this course, this is not a course in which is going to make you pass an all India exam. This is something which is not the aim of this course. Okay. So, here we will use the book of Spivak partly, not fully, to discuss what is a continuous function. When we were speaking about limits, when we wrote this statement, we did not bother whether f was defined at a or not, but suppose luckily a is defined at a, f is defined at a, sorry. So, if f is defined at a, and we have limit f(x) as x tends to a is f a, then and only then we call the function f to be continuous. To be continuous at a. Of course, if you want to say it is continuous over the whole real line or over the whole domain of definition of the function, then we are of course, the natural way to extend this idea is that we define the continuity, we expect the function to be continuous at each and every point. Now, again you see that here we are talking about a limiting procedure. So, once I can talk about a limiting procedure, I can of course have an epsilon delta description of a continuous function. Examples of continuous functions are abundant. Mathematics is actually the story of continuous function, analysis is the story of continuous functions, because there are functions for which are not continuous and they can have discontinuity at a certain point, some jump, some oscillation, right. So, limit existing does not at all mean continuity. Now, we will discuss that issues about discontinuities later on, but then how do I translate this into a statement in terms of epsilon delta? Very roughly speaking, in a very crude sense, continuity simply means a small change in x must give a small change in y, in the sense that if I want to draw the graph of functions. So, you see, drawing graphs of functions is something I urge you to spend some time with. Those who love mathematics, I tell you that is a much better thing than being hooked up to video games and other devices through the internet, other games through the internet. You can actually use the net to do the graphing. So, for example, if I can draw a function without lifting my hand from the plane of the board, I like to call such functions as continuous. But there is little subtlety here in the sense that every function may not be graphed so nicely, and continuity of functions, for example, there we will soon give examples where functions could be just continuous at one point and not continuous at any other point. Okay. Now, this again, the idea is that a small change here in x, if this is an x and if I move a little bit, if this is my x and if I move a little bit to these two sides, then you see the functional change in the function value. The change in the function value is not also very high. It is not that suddenly there is a jump. So, translated into the epsilon delta language, it says that given, so I am writing the limit, the definition I have for this, but instead L, it has now become f of a. Given epsilon greater than equal to 0, there exists delta greater than 0 such that for all x with we have now you might ask me, what about strictly bigger than 0 here, which was in the definition of the limit. The idea here is that here x can take the value a, and that is why it is defined at fa. So, it does not matter here that here we do not consider anymore a punctured neighborhood, because here x can take the value a, because I can compute the f values there. So, when I am talking a limit x tends to a, even if I do not have any, the function may not be defined at a, but I am expecting that at least in a neighborhood around a, all for every x the function value is well defined. So, this is the very basic definition. So, there are two things which you can immediately prove by using the epsilon delta definition about continuous functions, two things which I would now leave separate for you. For example, f is continuous and g is continuous implies f plus g is continuous. Similarly, if f is continuous and g is continuous, so if this is my data, then I will have f into g, which is fx into gx when you evaluate it, is continuous, right. So, the function f plus g is continuous and f product f g is continuous, and f by g is continuous if g not equal to 0 throughout for all x in the domain. So, that is something very standard, and so we are not going to get into any detailed proof. Now, look for example the function fx. Is it continuous? Oh, of course, it cannot be a continuous function at say at x equal to 0, because at x equal to 0 the function is not defined. Does the limit exist for it? Does limit sine of 1 by x, x tends to 0, this exists? The answer is no, because sine 1 by x keeps on oscillating as x approaches 0. It does not come to a stable value, right. So, in this case the answer is no, the limit does not exist, there is no limit, it does not exist. Now, if I take a function which you have already looked into in the previous classes, fx is equal to x sin x. So, you know that x equal to 0 is not in the domain, but what we had shown using the epsilon delta technique in the last class was that if you take the limit as x tends to 0, x sin 1 by x is actually 0. That is what we had shown. If you remember the graph, I just want you to recollect it. So, here we have drawn the lines y equal to x and y equal to minus x, and the graph essentially looks something like this. So here the function is not defined at x equal to 0, it is clear, and hence there is some sort of a discontinuity there. So, continuity cannot be defined in this way, but here we can remodel the function or redefine the function in the following way. Because I know that it is going to 0, this definition, let me define f(x) now as a function which is defined as x sine 1 by x when x is not equal to 0 and is defined as 0 when x is equal to 0. So, once I define it like this, then immediately I know that f0 is 0. So, this is nothing but f0, and hence the function is continuous at 0. So, I have redefined the function and the redefined function is now continuous. So, in such a cases where you can redefine a function a little bit, basically the point where the function is discontinuous, and if a limit exists as the x values approaches that point, then if I take that particular that limit value as the value of the function at that particular point, then I can actually remove the discontinuity at that point. That is called removable discontinuity. So, what we did is basically we removed the discontinuity. So, removable. So, but every discontinuity is not removable. For example, if you define a function like if you look at this function, so till 1 it comes to 1 like this, and then from 0, so f0 here is not 1, f0 is 0. So, there is a discontinuity here, and here this discontinuity cannot be removed because the limit as x tends to 0 from the right is 0, but limit of the function value as x tends to 0 from the left is 1. So, because the limit does not exist at the point x equal to 0, here the limit does not exist at the point x equal to 0. So, which means at that point the discontinuity is not removable. So, this is an example of removable discontinuity, and this is the case where discontinuity cannot be removed. Now, I will give an example of a function, an interesting one though, which will show that it is continuous only at one point and discontinuous at every other point. Its continuity is not valid for any other point other than 0. So, we define that f(x) is equal to x if x is rational and is equal to 0 if x is irrational. So, if you take any point other than 0, any a not equal to 0, then limit f(x) as x tends to a does not exist. Why? Because the function values keep on oscillating. So, wherever you are coming, it is basically, so you would take the value say a, and a is rational. A is q, then the function value is a at that point. So f of a is a, but in that neighborhood there are infinite values where f of a is 0 and where f of x is 0 and f of x is a. So, you cannot say that I can always, so here what would happen, you cannot say that I can, given whatever, however near the points I take, in this particular case, because of this oscillation, given any epsilon, I cannot always find a delta for which that relation of limit would hold true. If you want to if you don't find thinking in epsilon delta might be difficult, just think of a point which is non-zero and the function at every point, if it is rational, there will be only for any neighborhood around a point A, suppose even if it is rational, any neighborhood only there are countable many rational points, uncountable many irrational points. So, what happens is that the function value keeps on simply oscillating between some value of x and 0, x and 0, x and 0, x and 0. It just it is not possible to stabilize that movement, and that is why limit does not exist. But if you take this particular issue when f(x), limit of f(x) when x tends to 0, it does not matter whether we are looking at x is rational and x is not rational. If x is not rational, it is anyway 0, but if x is rational, as I go near 0 from both sides, the function value goes towards 0. So, when the limit of this function at 0 is 0, and this is nothing but f0 because 0 is a rational number, because f(x) is equal to x if x is rational. So, f0 is 0. So, which means at no other point a with non-zero, the function has a limit which is the function value. So, there is not continuous at, it does not have a limit. So, no question of continuity, it is not continuous at x equal to any a equal to not equal to 0, but only continuous at the point x equal to 0. Here is an example of a function which is continuous at a point, but not continuous on the whole real line. This is a very, very important result, example which I am giving from Spivak, and I think this is a very, very important thing. Now, there are certain cases, for example, it becomes difficult to, as Spivak shows, that it is very difficult to decide on the continuity of functions such as this. It might look quite obvious, oh it looks continuous, looks nice, but behind the idea that this function is continuous has an idea of composition of functions, because this function can be written in the following. So, first we apply the function g on x and then apply the sine function. So, if I take my f as a sine function and g as a squaring function, then f compose g is nothing but sine of x square. So, you first take the x, then you square it. So, that will give you g of x, and then you apply f on it, which will be sine of x square. So, if two functions, but individually sine is a continuous function and individually g is a continuous function. So, if I look into the sine of, if I look into the sine function and the square function individually, they are continuous, but if I compose them, will they remain continuous? That is, if f is continuous on say R, making a mistake. If G is continuous on R and F is continuous on the range of G, then F compose G is continuous on R. So, this is a result which appears absolutely simple, but then you can actually go ahead and prove it. You have to understand the continuity of F is not on R, but it is on the range of G, because F is acting on the range of G, because F compose G means F of Gx. So, F compose G, if you know this thing, it means F of Gx. So, this is exactly what is going to happen. I do not want to get into an epsilon delta proof of this, because nothing would happen if you, it is nothing great that I should be putting my time to prove this. This is something I should leave you to handle around. You can just play around a bit with this epsilon delta business, and it is very easy that this result will come in. What is possibly more important now is to understand here why I am talking about convexity, about the function, etc. I have never defined where is the function being defined from. Essentially, implicitly in all these definitions, I have been talking essentially of functions from R to R. But no matter how much we want to restrict ourselves to R to R, there are very majority classes of function which has to be defined over a smaller domain. So, essentially a more general idea is usually to study functions from a closed interval a b to R. But when you are talking about closed interval a b to R, you should be forewarned that here we are, when you are talking continuity, we are talking continuity only in the points interior to A and B. That is in at all points other than A and B, we are essentially talking about continuity in this sense. But when we are talking about the point A and point B, we are essentially talking about left and right continuity. So, limit in this particular case f x as x tends to A plus, because it comes from the right side, it should be f of A, that is right continuity, and then there is left continuity because with B it goes from the left. So, x goes to B minus. So, this means I am coming to B from the left, f x should be f b. So, whenever I am telling that a function is continuous over the closed interval a b, you should be careful enough to understand that at the end points I am only talking about left and right continuity, because I do not know anything about the nature of the function beyond the interval a b. Okay, if you say I know about the nature of the function on an open interval beyond the interval a b and I am just restricting it to a b, then it is obvious that I already know it is continuous on A. So, but if you do not know anything at the end points, this is the meaning of continuity, left and right continuity. Of course, by the whole definition of the limit, you might ask me that the notion of limit is valid, a notion of continuity is valid when this limit exists, means right limit exists and left limit exists, means right continuity exists and left continuity also is there, and the left continuity limit and the right limit for the right part and the left part should be equal to f a. But when you are at the end points, this is what you mean by continuity, only the left part and the right part of the limit, you do not either the left part or the right part, because you do not have other things. Now, we are going to prove, and this has to be proved, a very important result about continuity, a very important result. It essentially shows the very nature of continuity. This is a key result, and this idea has been used even in very advanced research. This idea actually helps. So, these ideas which are there in the calculus or analysis, if you want to call it for a moment, is so ingrained in the mathematical psyche or psyche of mathematicians that these are the tools people want to use one after another. These are the tools people want to use continuously, and so we are going to now talk about a very important result which I want to write as a theorem. Theorem is the mathematician's way of telling you that he wants to state a very important result with important consequences. So, suppose f is continuous at a, maybe I do not bother, maybe let me just for the time being make the thing look much more simpler. Let f from R to R be a continuous function. CONT is my short for continuous and Fn is my short for function. Be a continuous function with f of a strictly bigger than 0, where so a is an element in R for which f of a is strictly bigger than 0. What I want to show that there exists a delta, then there exists a delta greater than 0 such that for all x with this property, that x is lying in the delta neighborhood of a, we have fx strictly bigger than 0. So, this is the consistency property of a continuous function, that if I am at a point A, which essentially should be in the interior of the domain of the definition, or even at it could be at the boundary, then we have to talk about the left and right intervals. So, if I have an A for which f of a is strictly bigger than 0, then for there is a delta neighborhood around A such that for every x we have f of x to be strictly bigger than 0, every x lying in the neighborhood. But if I change the delta, if I make it bigger, that story might just break. So, if you look at a continuous function like this, so here at this point, so it does not matter, f a could be bigger than 0, f a could be less than 0, strictly less than 0. If f a is strictly less than 0, this everything inequality will change. So, this is a and this is my f a, and f of a is strictly bigger than 0. Now, let me look into this interval. Look at this interval. So, this is a plus delta and a minus delta. In this interval, f of a still continues to remain greater than 0. In fact, the interval can be expanded also a bit, but maximum you can come here. Maybe you can expand it a bit here and expand it a bit on this side, not more. Because once you come a little bit more, you say, okay, I can extend, there is f a is greater than 0 on this side, but because you want to make the thing symmetric, that neighborhood, you have to make it symmetric on this side also, but then a negative part comes in. So, it is sorry, in this case I will just make the drawing a bit more better to bring in a negative part to tell you that this might not always happen. So, okay. Now, you see here f a is strictly bigger than 0, and now here for example, if I take a neighborhood of this length, I take a similar side this side. So, I will have a plus delta here. So, this point is my a plus delta, this point is my a minus delta, and here also the function value you see remains strictly bigger than 0. But I might say that, okay, this side I have more up to here, I see I have f a to be strictly bigger than 0, but here if I increase it to this side to this amount, then I have to increase the delta amount by also by this amount on this side, it should come here, but then it encompasses a function value which is equal to 0 and in fact less than 0. So, for every delta it cannot work, so it just works for a fixed delta. So, if I bring in delta 1 say, this is my delta 1. So, this is a minus delta 1 and then this will be a plus delta 1. So, in this case for this part, for every x f of a is strictly bigger than 0, but for this part of the neighborhood there is a part from which f of a becomes 0 and negative. So, here, so the result that it is only for a delta, there is some delta, that is the whole key idea here. It does not work for all the deltas, it works for only one delta or maybe more than, or maybe if you know for one delta you can keep on making it smaller, then it will work. So, basically there is a threshold value of delta beyond which this result will break down. So, if you increase the delta a bit, this result will break down. You will, of course, if you shrink it down, obviously you will have the same thing, but if you make it bigger, that thing will break down, and that's the key idea here. And this idea would be used in the next class to talk about something very important called the intermediate value theorem. These ideas are used at that point, right. Okay. So now because f is continuous, I would go and give a definition, basically this, that given any epsilon greater than 0, there exists a delta greater than 0 such that whenever I have x minus a strictly less than delta, strictly less than epsilon. Okay. So, I can just open this up a bit and write it in this form. Fx is lying between Fa plus epsilon, Fa minus epsilon. Okay. Now, so this is for any arbitrary epsilon, there will be a delta. So, choose epsilon equal to Fa by 2, because Fa is strictly bigger than 0, I can always choose epsilon to be Fa by 2, half of Fa, and this result, this epsilon strictly bigger than 0, corresponding to this epsilon there must be some delta. So, there exists a delta dash say, such that whenever x minus a is in the delta dash, that is in the delta dash neighborhood, I would have the following to be true. So, which means in this case what is happening here, I have Fa by 2 from here strictly less than Fx, strictly less than 3 by 2 Fa. So, this is true for all x with x minus a strictly less than delta dash. Now, this means, but f of a is strictly bigger than 0, f of a, so this is epsilon, this is nothing but the epsilon. So, this is strictly bigger than 0. So, for every x here which satisfies this, I have this. So, my required delta is this delta dash. Okay. So, f of x remains 0 within that neighborhood. Now, sometimes what happens, if I know about the continuity of a function just at one point, I can speak about the continuity of the function over the whole real line if we have some additional property, a very standard sort of example that comes in, I do not know, many books. So, this comes as an exercise in Spivak, but I think this is a very standard example. It is given in many books, I have seen in many books actually. They are given as examples also is the following. So, suppose a function is such that f of x plus y is f x plus f y. So, the function is from R to R and the function satisfies this property, this is called the additivity property. So, this is true for whatever x y you choose, it does not matter, whatever x y you take in R, this will always hold. If this happens, for example, take the line f x equal to x, this happens, f x equal to 3x, 4x, this will happen. Now, if f is continuous at x equal to 0, then this is actually a linear function, then f is continuous at any a element of R. So, how do I go about it? The first thing to observe is that first put x equal to 0 and y equal to 0. Then by very definition f of 0 plus 0 is f0 plus f0. So, which means f0 is equal to 2f0, which means f0 is equal to 0. This is something, this information is immediately observed. Secondly, so what do you mean by continuity at 0? It means, so given epsilon, given an epsilon greater than 0, there exists a delta greater than 0 such that whenever this holds, f of x minus f0 which is 0, mod of f x is less than epsilon. This is what happens, right. Now, take any point in, take any a strictly bigger than 0, sorry, I am making a mistake, a element of R. Now, take any epsilon. So, for that epsilon there exists a delta for which this happens. So, take the same delta, okay. Consider epsilon greater than 0 and let x be such that this is true. Now, this if you choose this epsilon will give me this delta because of the fact that it is continuous at 0. So, I will take the same delta and look at all points in that neighborhood from A, delta neighborhood of A. Now, I want to show that this will also be less than epsilon. How do I show that? Here again this fact will come to help. So, this can be written as f of x minus a plus a minus f a, right. So, this is equal to now what is this? I will apply this one. So, this can be written as f of x minus a plus f a minus f a. So, f a cancels and this is equal to f of x minus a. So, but this number x minus a, the absolute value of this is less than delta, and whenever I have any real number whose absolute value is less than, given that epsilon this absolute value is less than delta, f of that value is strictly less than epsilon because of the continuity at 0, because I am now applying this, instead of x I am writing x minus a here. So, this is strictly less than epsilon. So, what I found? So, f of x minus f a modulus of this is nothing but the absolute value of f of x minus a, which is strictly less than epsilon. So, from here I conclude that given this epsilon, whatever delta works for the 0 case, it will work for any other point A. So, here I have, so once a delta is known for the point x, given an epsilon, once a delta is known for the point 0, the same delta will work for the point A. So, this is a very, so you see how useful the epsilon delta definition is. Without this epsilon delta definition, it is not so easy to prove just writing the limit thing. It is a very it's a difficult game to prove this fact. So, epsilon delta definition immediately gives you the result, and that is why you should, rather than getting worried about what has happened, we should actually celebrate the power of mathematical thinking. Thank you very much.